Alright guys, welcome back. Last time we left off on the looking at intrinsic semiconductors and the value of electrons and holes that we find in an intrinsic semiconductors. We discussed the Fermi energy, the Fermi function, the Fermi Dirac integral, and now we're basically going to kind of finish up talking about that, and then we're going to get into something I think is more important, which is the effects of donors and acceptors in a semiconductor. So last week, just to recap, we graphed the Fermi function, which is this guy right here, and we have here, you can see the graph where this black line is the Fermi function, f, and then this dotted line is 1 minus the Fermi function, where the f Fermi function stands for probability of a state being occupied by an electron. 1 minus f is the plot of a state being not occupied by an electron. GC, this is our density of states in the conduction band and density states in the valence band. When we multiply the two together, we get this little graph right here. Again, this is G of C times F of E. And the volume, if we integrate over this whole volume right here, we get the number of electrons N right here. And similarly, and of course this is holes right here, which is GV of E 1 minus F of E, right? Just like that. So similarly, I'm not going to go through the whole derivation with holes. If you understood how to do this, the part with holes should be relatively simple. Not a whole lot changes. I do want to emphasize the fact that for intrinsic semiconductor, the Fermi level is constant. It's pinned usually at this spot EI right here. And I'm going to kind of go through a quick derivation on how to do that. Kind of make some room here. But so for P, real quick, it's going to be the very bottom of the conduction band, or valence band, which we can take as negative infinity, to the top of the valence band, which is EV. And that's going to be GV of E, density of states in valence band, times probability of empty state in the valence band, integrated through that whole space right there. And you can think of that as, here's my conduction, here's my valence band, here's my EG right here. And so we're basically, this is EV, and then it goes all the way down to negative infinity, right? And that's what we're integrating. In reality, our electrons are only about a few kT in terms of energy, a few kT from the top of the valence band, because actually when we plot it, it looks something like this, So just like that. Okay. So that's what we're integrating here. We find when we use the same Fermi Dirac integral and the same netta substitution that we did last time, we get something that looks like this. NV, that is the effective density of states in the valence band, E to the EV minus EI. EI, we went from EF to EI to note that EI is the Fermi level in an intrinsic semiconductor over KT. All right, so I'm going to put these two equations right over here, so we have those for reference, because we're going to be using those a lot, where N is equal to NCE to the EI minus EC over KT, and P is equal to NV E to the EV minus EI over KT for intrinsic. Right, so that's only for intrinsic. So that's how we get that right there. And furthermore, for intrinsic semiconductors, we know that for every electron there's a hole, so we can just say that N equals P equals Ni, which is our intrinsic carrier concentration. And we can say that Ni squared equals Np, which is equal to Nc NV E to the EV minus EI over KT times E to the EC, oh I'm sorry, that's a EI minus EC over KT times E to the EV minus EI over KT, and then we put that together, and I is equal to square root NC NV e to the, well, I have EI goes to 0, EI minus EI is 0, and then I get negative EC plus EV over KT. Now, what we can do in this case is we can reference, because we don't actually know, what the actual energy of this is. If you ever, one of the early things you learn in early modern physics, early quantum mechanics, is the fact that we can never find where actually an electron, is at any given state of time and energy and momentum, but we can find these changes in energies. So we can, if we can reference something, like if we set EV equal to 0, we can find it everything in terms of EC. Well, if this is EV and this is EC, well then, and EV is equal to 0, then EG is simply EC, just like that. This is our conduction band, this is our valence band, right? So if I set EV equal to 0, then what I have here is NI is equal to NC NV. Oops, forgot to put a 2 here because I square root both sides. Very important. How about that? E to the negative EG over 2KT. Another very important equation, so I'm going to go ahead and rewrite this over here. NI equals to NC NV E to the negative EG over 2KT. Okay, so what does that tell us? Is that if you have a large band gap, then you have a small intrinsic carrier concentration. Think of large band gap semiconductors like something used for power electronics, like gallium nitride. It's a very, very wide band gap, so without any doping or any outside energy, it's a really good conductor. I'm sorry, really good insulator. There's a very small amount of free carriers at equilibrium. So, and you think of something like germanium, I think the band gap is 0.66 electron volts. Zinc oxide maybe, it's a very, very small band gap. So it has a much larger intrinsic carrier concentration. So let me erase this. And there's one more quick derivation I want to do here, and that's to find the intrinsic Fermi level EI, right? So I know from before, N equals P equals NC E to the EI minus EC over KT, which is equal to NV E to the EV minus EI over KT, right? And so I take these two and I'm going to solve for I, right? So I'm going to move this over here, I'm going to move this over here, and I'm going to do a natural log on both sides. And I'm going to bring KT over, and I get KT natural log NC over NV is equal to, that's going to be EV minus EI minus EI plus EC over KT. Right. Oops, nope, KT's over there. Maybe I shouldn't jump ahead so fast. Rewrite this. KT ln NC over NV is equal to, if EV equals 0, we reference EV to 0, which means EC is just EG minus 2 EI. Right? Hope that makes sense. We set EV equal to 0 just as a reference, to normalize it, right? So I'm going to move this over here and divide by 2. So I get EI is equal to EG over 2 minus KT over 2 natural log NC over NV. And cool thing about natural logs is if I flip these two, this becomes a positive sign, so I can rewrite EI is equal to EG over 2 plus KT over 2 natural log, right? Let's flip them, NV over NC, right? So let's look at this right here. Now we have an equation for EI. EI is constant in an intrinsic semiconductor unless you dope it or add some kind of energy to it. So it's the band gap divided by 2 plus this term KT over 2 natural log NV over NC. Now remember the thing about NV and NC, well NV is proportional to the effective mass of a hole, the 3 over 2, and NC is proportional to the effective mass of an electron, to the 3 over 2, right? So these terms, this term right here is actually very, very small compared to this. You know, the only kind of fluctuations that we're going to have here is any large differences between MP and MN, basically. So really, you know, this is negligible, but we can modulate this second term by modulating effective mass. You know, different growth techniques, or you know, depending on the material, you're going to have different effective mass. You know, how do we use a different conduction band? You know, we want to switch to the light hole or the heavy hole. You know, once you get into more complex materials, you know, 3-5 materials, you can start doing stuff like that. But but in general, this is going to be the dominant term right here. You know, and so what we get here is EC, EV reference to 0, EI. The intrinsic Fermi level is approximately halfway between these two, or 1/2 the band gap from EV. So that's a good equation, but it's not really worth writing down because we're going to get into something a little bit different now. So you know, intrinsic semiconductors don't really do a whole lot for us for when we deal with devices. What we really want here is we want to, you know, make a device either N-type or P-types, so we can switch it on and off, so we can control current. You know, and how are we going to do that? You know, we notice that our solution space to this, if we consider an electron concentration, it's really just this this little spot right here. But what if we brought up the Fermi function and we brought it up to, say, here, right? I mean, you know, to here. You know, then we have a much larger space here, and this becomes significantly bigger, right? If we can raise this Fermi level up, which if this raises up, and that means you know, 1 minus F raises up, you know, and you know, this is our right there, and that's our new AF is right here, and then our whole concentration gets much smaller, right? But we can, you know, if we can find a way to raise this Fermi level up, you know, or this the Fermi function up, so when we multiply the Fermi function by the density of states, we get a larger amount of electrons. Then we have it becomes a much better conductor for electrons. You know, and similarly, if you wanted to conduct holes better, and we want more holes in there, then we need to find a way to bring this Fermi level 1 minus F down further, so then this can get better. But if you notice by looking at these graphs, if we bring the Fermi level up, this gets bigger, but this will get significantly smaller. You can follow my drawings. This is 1 minus F. This is F. You know, if I bring it down here, right, then this gets much bigger, right, and then this gets much smaller. So you can really only have one or the other, you know. So let's talk about how we're going to do that. We're going to talk about doping. Doping in semiconductors. So if you look at a silicon atom, in terms of its Lewis dot structure, it has 4 atoms. It is a group 4 element, right? So, inside a crystal lattice, when it's bonded with other silicon atoms, they all attach to each other via these electrons. Right? So here's each one of these lines represents 2 electrons. a bonding pair. Right? There we go. So that leaves very few. That leaves really no electrons to free electrons to go to the conduction band and generate electron current. So we got to find out. So what can we do to this to add an extra electron and increase the value of n, and thereby increase the electron conductivity. Well, if you look at let's look at a group 5 element on the periodic table. I'm sorry, silicon is group 5. Let's look at I'm sorry, yeah, group 5. Silicon is group 4. And let's look at a group 5 element, right? So that could be like phosphorus, right? Phosphorus Lewis dot structure has 1, 2, 3, 4, 5 electrons, right? And it takes only 2 electrons to make a bond between 2 atoms. So what if we somehow got this phosphorus atom in here, right? This electron would bond with another electron from the silicon, same with this one and this one and this one right here. But then you've got this extra electron which just kind of hangs there by a very weak force, very weak attractive force. And if the given energy of this phosphorus atom is, or this any group 5 element is close enough to the conduction band, then it only takes a small amount of thermal energy for this electron to break away from this phosphorus atom in the valence band, in the phosphorus valence band, and move into the conduction band of the bulk of the semiconductor. If you look at in terms of the energy bands, this is X, this is E, this is EC, this is EV, right? I'm just going to put our EI for reference. If we add some phosphorus atom with some donor energy, we call it ED, right? So just as before, the phosphorus atoms are in the valence band of these the phosphorus, and but given a small amount of energy, this EC minus ED, then this can just move to the valence band, right? And let's say each one of these electrons comes from one phosphorus atom, one group 5 atom. Well, then this phosphorus atom, right, which we'll call it P, right? It gives up this electron right here, and then it becomes positively charged, right? We have a hole here and an electron here. And if these are close enough, similarly, all these can move up here in the conduction band. Hence, we increase our number of electrons, n. If we increase the number of electrons, well, then we increase the probability that a state is occupied by an electron in the conduction band, and therefore our Fe should increase, right? And then what happens here is all these phosphorus atoms become ionized. They just become phosphorus plus, right? And so what we need for a good donor, we need 2 things. For one, we need it to be a group 5 element. If we're doing silicon, if we're doing compound semiconductors, it's a different process, which someday hopefully I will talk to you about. But if it's a group 5, we need it needs to be a group 5, and number 2, it needs to have an energy that's close enough to the conduction band such that only a very small amount of thermal energy, which any kind of diffusion processing that you do in a lab, usually there's enough heat supplied to do all of that. A lot of heat involved to do this stuff, but it should be more than enough to ionize all these atoms and bring these electrons into the conduction band. So that's more of a physical view, and now we're going to get into the mathematical part of it right here. So we want to get that Fermi level to go up, right? So we're going to introduce the Fermi function again, but we're going to make a little addition to it. So F of E becomes, I'm going to call it F of EF, because now Fermi level is going to change now that it's no longer intrinsic, right? 1 over 1 plus 1 over G E to the ED minus EF over KT. So this is the probability probability that a donor state will be occupied by an electron, right? Here's our donors. And we'll call this donor density ND, right? So the probability that this is occupied by an electron, right? So if we dope a semiconductor with some doping concentration ND, D stands for donor. We want to know not so much, if we want to know how much of these are ionized, what we want to know is how many of these are empty. So if these are empty, then that means it's ionized. So we actually want to, so this number here, whether or not these are, what's our density of ions, of donor ions, it's going to be our density of donors times 1 minus F of E. So we're not just thinking of this F up here, we're talking about this Fermi function that we kind of made a little change to here with this G and this ED. Our new energy is actually ED, not G, right? So if you look at this, to get as high a possible donor energy, let me rewrite this real quick. So then ND plus becomes ND over 1 plus GE to the E F minus ED over KT. Okay, just like that. And by the way, G is called the degeneracy factor, and it's usually got a value of 2, right? So think about it. If EF and ED are very close to each other, then this whole term becomes 0, right? Which means we just have ND over 1 plus G, right? Just like that, So we want these to be very close, and then this gives us a very large amount of ionization, right? So the other thing we want to talk about is charge neutrality, right? And that's the fact that in a uniformly doped semiconductor, no doping gradient, meaning that the doping is constant, across the whole semiconductor at any position, right? Then the charges everywhere at any point in the semiconductor should all be equal. That means all the positive charges should be equal to the negative charges, right? So that means that what are our positive charges? P plus ND plus. We have all these donors that become positively ionized every time they lose an electron to the conduction band. Is equal to our negative charges. Well, N is a negative charge plus Na minus. Similarly, we didn't really talk about this, but it should make sense. If we dope a semiconductor with a group 3 element, maybe boron, for example. Here's a silicon lattice. Boron. Well, boron, Lewis dot structure, has only 3 electrons, which means we have these bonds, right? But we have this, this is 1 electron, and then we have this absence of an electron. So I guess I shouldn't even draw a line here. We have this electron, and we have this absence of an electron, and that's your hole, right? So we want the energy of this donor, the energy of this acceptor, because it's accepting an electron from the valence band, right, to be very close to the valence band, right? So let's say it's boron, such that a small amount of thermal energy will take should take this electron here, move it up to here, and then we have B minus, because it has an extra electron, and here we have a hole, And a hole can be thought of as like, it's really just an absence of an electron in the valence band, And just like electrons, they're mobile, so they move through. They'll move to this spot, and this will move there, and they'll move this, and over, and it moves the same way. They generally have a lower mobility, which means they don't move as fast and as easily through a lattice as an electron. But nevertheless, they do move, and they do contribute to current. And in silicon, their mobility is close enough such that you can dope an N-type and P-type, and you can switch it to do different things, and that's why we have CMOS, is because of that. So that's EC, EV, EC, and that's EV, and this is our acceptor energy. Call that EA, right? And so that has the equation. Just pull this up here. So NA minus is equal to NA just F of E. But that can be, that can be written as 1 over 1 plus G E to the EA minus EF over KT, right? EA, the acceptor energy and the donor energy in this spot are constant. They're dependent on the atom that you're using as your donor or your acceptor. So those aren't going to change. Really, what we're looking for here, our unknown is EF. That's our unknown that we're looking for in this case. And when we go back to charge neutrality, now the important thing to remember from before is that in an intrinsic semiconductor, N equals P equals Ni, right? And Ni squared is equal to Np, just like that, right? So when we dope something, and this equation will actually hold through doping, and when we dope something high enough, or at a certain level such that all the donors will be ionized, which means that we don't dope it so high that that this equation isn't is going to be significantly less than 1, and our energy is significantly close to the conduction band, right? For a donor, we want to get 100% doping, so we want this to be as close as possible here, and we don't want to dope it so high that there aren't enough available states, in C, effective density states, that they'll fill up all those NCs, right? So we want to get 100% ionization, right? If you think about it, if you dope something, ND, and it becomes 100% ionized, then you have, your intrinsic electrons, Ni, plus the new electrons which have been generated from N. Well, if Ni is like, 10 to the 11, which is, I think that's what, Cm-3, which is pretty similar, I think that's what silicon is, right? And your donors are like 10 to the 17, 16, 17, something like that. 16, 17 is a pretty good number for silicon. Then you have 10 to the 17. 10 to the 17 extra electrons. Well, 10 to the 17 plus 10 to the 11, it's just 10 to the 17, right? Or it's like 1